Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. What comets are really made of? Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission which orbited and studied comet 67P/Churyumov-Gerasimenko from 2014 to 2016, provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the Sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the Sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the Sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the Sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the Sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward, and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the Sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment, the exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed. Why distant galaxies? Look red. When astronomers point their most powerful telescopes toward the deepest reaches of space, photographing galaxies billions of light years away, they notice something remarkable. These distant galaxies appear distinctly redder than nearby ones. Light that was emitted as ultraviolet or blue has been shifted toward red and infrared wavelengths by the time it reaches Earth. This redshift is one of the most important observations in all of astronomy, providing direct evidence for the expansion of the universe and allowing astronomers to measure cosmic distances and trace the history of the cosmos back nearly to the Big Bang itself. The primary cause of this reddening is cosmological redshift, a consequence of the universe's expansion. This phenomenon was first observationally established by Edwin Hubble in 1929, though the theoretical groundwork had been laid by several physicists, including Alexander Friedmann and Georges Lemaitre, who independently developed solutions to Einstein's equations of general relativity that predicted an expanding universe. Hubble observed that distant galaxies showed spectral lines, the characteristic fingerprints of elements absorbing or emitting light at specific wavelengths shifted toward longer, redder wavelengths. Moreover, he found that more distant galaxies showed larger redshifts, establishing what became known as Hubble's law. The recession velocity of a galaxy is proportional to its distance. The expansion of the universe is not like objects moving through space, it's space itself that's expanding. Imagine the universe as the surface of a balloon with galaxies painted on it. As you inflate the balloon, the surface stretches and the distance between any 2 points on the surface increases. The galaxies themselves don't move through the rubber. The rubber itself expands, carrying the galaxies apart. This is fundamentally different from regular motion through space, and it's this expansion of space that creates cosmological redshift. When a galaxy emits light, that light begins its journey through space toward Earth. The light consists of electromagnetic waves, oscillating electric and magnetic fields propagating through space. As the light travels, the space through which it's traveling is expanding. This expansion stretches the wavelength of the light. Imagine a wave painted on a rubber band. If you stretch the rubber band, the wave gets stretched too, its wavelength increasing. The same thing happens to light traveling through expanding space. Light that began as ultraviolet with a wavelength of 300 nanometers might arrive at Earth as visible red light with a wavelength of 600 nanometers if it has traveled through enough expanding space. The amount of redshift depends on how much the universe has expanded during the light's journey. Astronomers quantify this using the redshift parameter, represented by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. Wavelengths have stretched by a factor of 2. A redshift of Z equals 2 means the universe has tripled in size. Wavelengths have stretched by a factor of 3. The highest redshift galaxies yet observed have redshifts around Z equals 13 to 14, meaning the universe has expanded by a factor of about 14 or 15 since those galaxies emitted the light we now detect. These galaxies existed when the universe was only a few 100 million years old, less than 3% of its current age. For nearby galaxies, the redshift is small, perhaps Z equals 0.01 or less. The Andromeda galaxy, our nearest large galactic neighbour, actually shows a blue shift rather than a redshift, because it's moving toward us through space faster than the cosmic expansion is carrying it away. But for galaxies more than a few 100 million light-years distant, cosmological redshift dominates, and the farther the galaxy, the larger the redshift. This relationship between distance and redshift allows astronomers to use redshift as a distance indicator. By measuring the redshift of spectral lines in a galaxy's light, they can calculate how far away it is and how long ago the light was emitted. A galaxy at Z equals 1 is seen as it was about 8 billion years ago, when the universe was roughly half its current age. A galaxy at Z equals 6 is seen as it was less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first generations of stars were forming. Redshift affects all wavelengths equally, in terms of the stretching factor. Ultraviolet light gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into far infrared and eventually into microwaves. For the most distant galaxies, light that was emitted in the ultraviolet, the signature of hot, young stars, arrives at Earth as infrared radiation. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the early universe. They can detect the stretched light from the most distant galaxies, galaxies so far away that their visible light has been redshifted entirely out of the visible spectrum. There's another related effect that makes distant galaxies appear redder beyond just the stretching of wavelengths. As light loses energy through redshift, longer wavelengths mean lower energy. The apparent brightness of the galaxy dims. A galaxy at high redshift appears fainter than it would if there were no cosmic expansion. Additionally, the rate at which photons arrive is reduced. If a galaxy emits 1 photon per second toward Earth, but the universe doubles in size during the light's journey, Those photons arrive spread out over 2 seconds because the space between them has been stretched. This reduces the detected brightness even further. The cosmic microwave background radiation provides the most extreme example of cosmological redshift. This radiation was emitted when the universe was 380,000 years old, at a temperature of about 3,000 Kelvin. At that temperature, matter emitted primarily visible and infrared radiation. The redshift since that time is about C equals 1,100, meaning the universe has expanded by a factor of 1,100. Wavelengths have been stretched by the same factor, so light that was visible orange or red has been stretched into microwave radiation. The temperature corresponding to this radiation has dropped by the same factor, from 3,000 Kelvin down to 2.7 Kelvin today. It's important to distinguish cosmological redshift from Doppler shift, though they're related and can sometimes be confused. Doppler shift occurs when a light source moves through space toward or away from an observer. An approaching object's light is blue shifted, compressed to shorter wavelengths, while a receding object's light is redshifted. This is the effect that changes the pitch of a siren as an ambulance approaches and then passes you. For galaxies with relatively small redshifts, say Z less than 0.1, cosmological redshift and Doppler shift give nearly identical results and can be treated interchangeably for many purposes. But for high redshifts, the distinction matters. Cosmological redshift is fundamentally about the expansion of space itself, while Doppler shift is about motion through space. Redshift also allows astronomers to study the history of cosmic expansion. By measuring redshifts of many galaxies at various distances and determining their distances through other methods, like standard candles, objects of known intrinsic brightness, astronomers can trace how the expansion rate has changed over cosmic history. These studies revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, made by studying distant supernovae and measuring how their redshifts and distances deviated from what would be expected in a universe with constant or decelerating expansion. The acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy density and exerts a kind of repulsive effect that pushes space apart. This dark energy's influence has grown over cosmic time as the universe expanded and matter became more dilute. In the early universe, matter dominated and the expansion was slowing down. But a few billion years ago, dark energy became dominant and the expansion began accelerating. Distant galaxies' redshifts encode this history, showing patterns that reveal when the transition from deceleration to acceleration occurred. Redshift measurements also reveal structure in the universe. When astronomers measure redshifts for thousands or millions of galaxies, they can create three-dimensional maps showing how galaxies are distributed in space. These maps reveal the cosmic web, the filaments, walls, and voids that constitute the large-scale structure of the universe. Regions where galaxies are closely spaced show similar redshifts because they are at similar distances. Voids show up as redshift ranges where few galaxies appear. The chemical evolution of the universe is written in redshift as well. Spectroscopy of distant galaxies reveals what elements were present when that light was emitted billions of years ago. By comparing galaxies at different redshifts, different cosmic times, astronomers can trace how the abundance of heavy elements has increased over cosmic history as successive generations of stars created these elements through nuclear fusion and dispersed them through supernova explosions. Galaxies at Z equals 6 or 7 show much lower abundances of elements heavier than helium compared to nearby galaxies, confirming that the early universe was primarily hydrogen and helium, with heavy elements accumulating over billions of years. Even the shapes and types of galaxies change with redshift. High redshift galaxies tend to be smaller, more irregular, and more actively forming stars than low redshift galaxies. This reveals that galaxies evolve over time, growing through mergers and gradually building up their stellar populations. The universe at c equals 2, when it was about 3 billion years old, was a much more turbulent place, with higher rates of galaxy interactions and star formation than the relatively sedate local universe we see today. Gravitational lensing affects redshift measurements in subtle ways. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity bends the light's path and can magnify the image. But it also affects the light's frequency. Different images of a gravitationally lensed galaxy, formed by light taking different paths around the lensing mass, can show slightly different redshifts due to the gravitational time dilation in the lens's gravitational field. These tiny differences help astronomers probe the distribution of mass in the lensing object. The reddening of distant galaxies is therefore not just an interesting observational fact, but a fundamental window into cosmic history. Every measurement of a galaxy's redshift tells us how far away it is, how long ago its light was emitted, and what the universe was like at that cosmic epoch. The systematic increase in redshift with distance directly demonstrates that the universe is expanding, that it had a beginning in the Big Bang, and that it's evolving over time. The precise pattern of redshifts reveals the expansion history, constrains the properties of dark energy, and allows us to trace the formation and evolution of structure across billions of years of cosmic time, making the reddening of distant galaxies one of the most information-rich phenomena in observational astronomy. Why some planets have no moons. Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons, while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers. But these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small Hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small Hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the sun, or get ejected from the system entirely. The closer the planet is to the sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are three primary mechanisms: co-formation, where the moon forms from the same disk of material as the planet; capture, where the planet's gravity snares a passing object; and giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon, or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger Hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter. Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across, and Deimos about 12 kilometers. Mars likely captured them during the early solar system, when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely formed their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young sun. These disks contained enough material to form multiple large moons. Jupiter's four Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions, the features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, these bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line, but Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear. It converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible. Hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors. Larger tidal forces lock a moon more quickly. Closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the moon had already been showing the same face toward our planet for billions of years. Tidal locking doesn't just affect the moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet, because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the Moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the Moon's orbital period. At that point, Earth would be tidally locked to the Moon, just as the Moon is now locked to Earth, with the same face of Earth always facing the Moon. However, this will never happen because the Sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the Moon. The expanding Sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the Moon has significant consequences for lunar exploration and observation. The far side of the Moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called maria that dominate the near side's appearance. This asymmetry likely relates to the Moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the Moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the Moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the Moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The Moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time. What's left after a star explodes? When a massive star reaches the end of its life and explodes in a supernova, the detonation is one of the most violent events in the universe, releasing in a few seconds as much energy as the Sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blasted into space at thousands of kilometers per second, creating an expanding shell of hot gas enriched with newly forged elements. But the explosion doesn't simply obliterate the star. At the center of the expanding debris, something remains, a compact, incredibly dense object created from the collapsed core. What gets left behind depends on the mass of that core and determines whether the remnant becomes a neutron star, a pulsar, a magnetar, a black hole, or in rare cases, nothing at all. The immediate aftermath of a core collapse supernova leaves behind a proto-neutron star, an extremely hot, dense ball of neutrons about 20 to 30 kilometers in diameter, containing between 1.4 and about 3 solar masses compressed into a volume smaller than a city. The temperature at birth exceeds 100 billion degrees Celsius, making it one of the hottest objects in the universe. Over the next 10 to 20 seconds, the proto-neutron star cools by emitting enormous numbers of neutrinos, ghostly particles that barely interact with matter but carry away 99% of the supernova's energy. As the proto-neutron star cools and stabilizes over minutes to days, it becomes a neutron star, a stellar remnant held up against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons being compressed too closely together. The density is extraordinary, about 500 million tons per cubic centimeter, comparable to compressing all of humanity into a volume the size of a sugar cube. A neutron star is essentially a single gigantic atomic nucleus, held together by gravity rather than the strong nuclear force. The structure of a neutron star is layered and complex. At the surface lies a thin atmosphere, only centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, about a kilometer thick, where matter exists as a crystalline lattice of atomic nuclei, extremely neutron-rich nuclei unlike any found on Earth, embedded in a sea of electrons. These nuclei become increasingly neutron-rich with depth, containing far more neutrons than protons. Deeper still, at the interface between outer and inner crust, neutrons begin to drip out of nuclei, creating a neutron superfluid that coexists with the nuclear lattice. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever, a quantum mechanical phenomenon that can only occur at extremely low temperatures or extremely high densities. In neutron stars, despite the enormous temperatures by human standards, the density is so extreme that superfluidity occurs. The inner crust, extending to about 10 kilometers depth, consists of increasingly exotic arrangements of nuclei and superfluid neutrons. Computer simulations predict that nuclei might arrange into cylindrical rods, flat plates, or even more complex three-dimensional structures, nicknamed nuclear pasta, because of their resemblance to spaghetti, lasagna, and other pasta shapes. This nuclear pasta might be the strongest material in the universe, billions of times stronger than steel. Below the crust lies the outer core, where nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. Both the neutrons and protons exist in superfluid and superconducting states respectively. The protons form a superconductor, where electrical currents can flow without resistance. This region makes up the bulk of the neutron star's mass and extends to perhaps 10 to 12 kilometers from the center. At the very center, in the inner core, where densities exceed that of atomic nuclei by factors of 2 to 10, matter might exist in states never observed in laboratories. Neutrons themselves might break down into their constituent quarks, creating quark matter or strange quark matter. Other exotic particles predicted by quantum chromodynamics, the theory describing the strong nuclear force, might appear, including hyperons, kaons, or pion condensates. The exact nature of matter at these densities remains one of the great unsolved problems in physics, accessible only through observations of neutron stars and theoretical calculations. Many neutron stars are born rotating rapidly, spinning tens or hundreds of times per second, inheriting and concentrating the angular momentum of the massive star's core as it collapsed. If the neutron star's magnetic field is tilted relative to its rotation axis, which is common, the neutron star becomes a pulsar. The magnetic field, enormously compressed and amplified during the collapse, can reach strengths of 1 trillion times. Earth's magnetic field. Charged particles accelerated along magnetic field lines near the poles emit beams of radiation that sweep through space like a cosmic lighthouse. When one of these beams sweeps across Earth, we detect a pulse, hence the name pulsar. The pulses arrive with extraordinary regularity. The Crab pulsar, formed in the supernova observed in 1054 AD, rotates 30 times per second. The fastest pulsar known, PSRJ 1748-2446 AD, discovered in 2006, rotates 716 times per second, so fast that its equator is moving at about 24% of the speed of light. At these rotation rates, the neutron star bulges significantly at its equator but holds together through its tremendous gravitational binding and the strength of neutron-degenerate matter. Pulsars gradually slow down over millions of years as their magnetic fields radiate energy and carry away angular momentum. The rate of slowdown reveals the pulsar's age and magnetic field strength. Young pulsars like the Crab slow down noticeably over human timescales. the Crab's rotation period increases by about 38 nanoseconds per day. Old pulsars slow down much more gradually and eventually become too slow to generate detectable pulses, though the neutron star continues existing as a dark, cooling ember. Some neutron stars are born with even stronger magnetic fields, up to 1,000 times more intense than typical pulsars, reaching magnetic field strengths of 10 to the 15th Gauss. These objects are called magnetars, and they're the strongest magnets in the universe. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms become elongated into needle-like shapes. The magnetic field stores so much energy that magnetars occasionally undergo starquakes, sudden rearrangements of the neutron star's crust that release tremendous bursts of X-rays and gamma rays. The magnetar SGR 1806-20 released a giant flare in 2004 that briefly saturated instruments across the solar system despite being 50,000 light-years away. Not all neutron stars become pulsars. If the magnetic field happens to be nearly aligned with the rotation axis, the beams don't sweep across our line of sight, and we don't see pulses. These objects, often called radio-quiet neutron stars, or simply isolated neutron stars, are much harder to detect. They can only be found through their thermal emission. They're hot enough, at temperatures of a few million degrees, to emit X-rays. The Hubble Space Telescope and X-ray observatories have identified several dozen of these isolated neutron stars, though many more certainly exist undetected. Binary systems where a neutron star has a companion star create unique situations. If the companion is a normal star and the orbit is close enough, the neutron star's gravity can pull material from the companion. This material spirals inward through an accretion disk, heating to millions of degrees and emitting intense X-rays before crashing onto the neutron star's surface. These X-ray binaries can be incredibly luminous, sometimes outshining entire galaxies in X-rays. The infalling material also carries angular momentum, spinning up the neutron star. Over millions of years, an old, slow-spinning pulsar can be recycled into a millisecond pulsar, rotating hundreds of times per second, rejuvenated by mass transfer from its companion. When two neutron stars orbit each other, they form a binary neutron star system. Objects like the Hulse-Taylor binary, discovered by Russell Hulse and Joseph Taylor in 1974, which earned them the 1993 Nobel Prize in Physics. These systems emit gravitational waves, ripples in spacetime that carry away orbital energy. As they lose energy, the neutron stars spiral closer together. Eventually, after millions or billions of years, they merge in a catastrophic collision. The merger produces intense gravitational waves, events that LIGO and other gravitational wave observatories have detected, along with a kilonova, a spectacular explosion that creates heavy elements like gold and platinum through rapid neutron capture. The merger of two neutron stars can produce different outcomes depending on the total mass. If the combined mass is below about 2.2 to 2.9 solar masses, the exact threshold remains uncertain. The merger might create a more massive neutron star, though one that's likely unstable and will soon collapse. If the total mass exceeds this threshold, the merger immediately creates a black hole, with no stable neutron star phase at all. The LIGO detection in 2017, designated GW170817, appears to have created either a hypermassive neutron star that collapsed within seconds or a black hole directly. If the collapsing core of a supernova exceeds about 2.2 to 3 solar masses, again, the exact threshold depends on the poorly known equation of state of nuclear matter. Neutron degeneracy pressure cannot halt the collapse. Nothing known in physics can support the core against its own gravity. The collapse continues, compressing matter to infinite density at a point called a singularity, surrounded by an event horizon from which nothing can escape. The stellar remnant becomes a black hole. The supernova explosion might proceed normally, leaving a black hole at the center of the expanding debris. Or if the core is sufficiently massive, the collapse might be so catastrophic that it swallows the infalling material before an explosion can develop, creating a black hole with little or no visible supernova, a so-called failed supernova. Stellar mass black holes created from supernova typically contain 5 to perhaps 20 solar masses. They're invisible except through their gravitational effects and the radiation from material falling into them. In X-ray binary systems, black holes reveal themselves through the extremely energetic X-rays emitted by infalling material, distinguishable from neutron star systems by the absence of pulsations and by the inferred mass. Anything above 3 solar masses cannot be a neutron star and must be a black hole. Some supernova types leave nothing behind at all. Pair instability supernova occur in extremely massive stars, those with initial masses exceeding about 130 solar masses. In the cores of these giants, temperatures and photon energies become so extreme that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is obliterated. No neutron star, no black hole, just an expanding cloud of debris. These explosions were more common in the early universe, when stars could grow more massive due to lower metallicity, but they might still occur in regions with primordial composition. The observable supernova remnant, the expanding shell of gas and dust, evolves over thousands to tens of thousands of years. Initially, the blast wave plows through the surrounding interstellar medium at thousands of kilometers per second, creating a hot, shock-heated region. The Crab Nebula, the remnant of the 1054 supernova, is still expanding at about 1,500 kilometers per second. The pulsar at its center powers the nebula's glow, creating a wind of relativistic particles that illuminate the expanding gas. Older supernova remnants like the Cygnus Loop, about 10,000 years old, have expanded to hundreds of light years across. The blast wave has slowed to tens of kilometers per second, and the shock is transitioning from adiabatic expansion, where the remnant retains its heat, to radiative expansion, where the shocked gas cools and radiates energy away, creating the delicate filaments visible in optical and X-ray images. Eventually, after perhaps 100,000 years, the remnant merges with the surrounding interstellar medium, its expansion slowing to match the general motion of gas in the galaxy. The enriched material, oxygen, carbon, silicon, iron, and other elements forged in the star and the explosion, mixes into interstellar clouds. These enriched clouds eventually collapse to form new generations of stars and planets, incorporating the elements created by the previous stellar generation. Every atom of oxygen you breathe, every atom of carbon in your body, was created in a star and dispersed by a supernova, later incorporated into the molecular cloud from which the Sun and Earth formed. What's left after a star explodes depends on the fine details of mass, composition, rotation, and magnetic fields, whether the core becomes a neutron star or black hole, whether the neutron star becomes an observable pulsar or remains radio quiet, whether the magnetic field is ordinary or reaches magnetar strength. Each stellar death creates a unique remnant, a compact object encoding in its properties the history of the parent star and the violence of its death, objects that will persist for trillions of years after the last stars have formed, cooling slowly in the expanding universe, monuments to stellar death that simultaneously mark endings and beginnings in the grand cycle of cosmic recycling. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much, and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where 2 stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from 2 suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets and the basic ingredients for life. Elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life, adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, chlorophyll uses 2 photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Ion compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Ion photosynthesis might precipitate iron oxides, organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions. Other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons, and releasing two protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1 million times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars.